On Wednesday, we were talking about taking the divergence of the electric field, and this video is going to build off of that and talk about using Gauss's law in various ways. So on Wednesday, we were looking at this divergence of the electric field using the nabla operator, the del operator, and when we take the divergence, this del operator dotted with the E field, we saw that we can use this expression for the E field that we talked about before, the Coulomb integral. And when we do this divergence, we end up with these delta functions that we talked about a little bit last time. And these delta functions that are very special, that they select a very specific value for that function. And what we end up with is we end up with this charge density at the location xyz, which, if you remember, this location up here that we have right here that's designated by the R, that's really just a shorthand notation for saying a coordinate in 3 space. So we can also designate that as xyz. And so what this gave us is Gauss's law, that we have the divergence of the electric field is equal to the charge density divided by epsilon naught. And this is a really powerful relationship. And essentially what this means is, before we had the Coulomb integral, which I'll just go back one screen to look at this. Before we had this Coulomb integral here, and this meant that if we knew the charge density at all locations, then we could integrate this function that's related, that this product of charge density with the location information, and that would give us the electric field at any location. Now what we're saying is, if we know the electric field at any location, designated by vector r, then taking the divergence of that electric field will tell us the charge density at that location. Positive divergence indicates a source, so if we have any positive charge at a location, we will get a source of the electric field. Any negative charge will be a sink for the electric field. So this is a really great relationship, and as we go through the rest of the course, we're going to see that this is really, really important. Now, what we want to look at next, though, is how do we relate this expression that I've called Gauss's law to the Gauss's law that you've seen before and that you've used in introductory E&M and places like that. And as we were talking about at the end of class on Wednesday, that Gauss's law involves some sort of surface, it involves some sort of electric flux, it involves some sort of total charge within that surface, the charge enclosed. And so now we're going to look at how these are related. And the relation between them has to do with the fundamental theorem of calculus. And by the way, these slides are the same slides, picking up from the slides on Wednesday. So I just skipped over a couple things about the units of the delta function, but this PDF is all posted on Blackboard, so you should be able to find that. Anyway, so the fundamental theorem of calculus, I'm sure you've all heard of it before because you've taken calculus, and as the name implies, this is fundamental, right? This is something that's really important in calculus. And basically all it says is that if you take the derivative of a function and then you take the integral, then you end up with the function itself. Specifically, you get the same function back evaluated at those limits of integration. So in this case, in this one-dimensional function f, we take the derivative with respect to the variable x, we then integrate with respect to x from a to b, and we get the value of f at b minus the value of f at a. So we get the function f evaluated at the boundaries. Now with the electric field, now we're dealing with a function that exists in 3 dimensions. We're taking the 3-dimensional vector derivative of that function. We're then taking an integral over a volume of that function. And when we apply the fundamental theorem of calculus to this, we end up with the function e evaluated at the boundary of that integral. Now for a 3-dimensional space, though, the boundary of a 3-dimensional space is that outer surface. And so that's where this idea comes from, this closed boundary surface, that this is the outer surface of some three-dimensional volume. So let's say we have some sphere here, and we will see if I'm able to draw anything even close to a sphere. Look at that, that's not too terrible. So let's say we have a sphere, and the whole inner region of that sphere, anything that's inside here, is part of this volume. And it has a volume, if it's a sphere, it has a volume of 4/3 pi r cubed. And so any point within that volume would show up in this integral over here. But the outer surface, that has an area of 4 pi r squared, that outer surface is what we'd be integrating over on this right-hand side. And we have the circle in the integral to indicate that it's a closed surface. So this is something that's known as the divergence theorem. Sometimes I think it's also known as Gauss's theorem, although I might be mixing that up, to be perfectly honest. But I know it's definitely known as the divergence theorem. But it's essentially an application of the fundamental theorem of calculus. Now, what we can do with this, looking at, going down to the rest of this screen, we now have this right-hand side, which this is the integral of the electric field over some area. Well, that is electric flux. So this is the total flux into or out of this outer surface. And what this is saying is that on the left-hand side now, we apply what we just used for Gauss's law, that this divergence of the electric field becomes charge density divided by epsilon naught. That's Gauss's law from what we saw on the previous screen. If we take epsilon naught out of the integral, that's just a uniform parameter, so that can come out of the integral. We're left with an integral of rho over some finite volume. And I will clarify that we're talking about finite volumes of space right now. So we're taking the integral of rho over a finite volume, and taking the integral of rho, well, rho is just charge per volume, so we integrate that over a volume and we get total charge, in this case capital Q. So the total charge Q within this volume V that I've designated by this script V. And what we have here is that this ratio of the total volume, or the total charge within that volume divided by epsilon naught, is equal to the total electric flux going out of that surface or into that surface. If Q is positive, it would be a net flux out. If Q is negative, it would be a net flux in. And if Q is 0, then it would be no net flux. But just to clarify, no net flux does not necessarily mean no flux at all. For example, if you had a positive charge and a negative charge, you could have electric field lines that go out part of the surface and then come back in. So the net flux would be 0, but you would still have local regions that would have some flux. But anyway, this is most likely the form of Gauss's law that you are more familiar with, that the integral of E over a closed surface is equal to the charge enclosed by that surface divided by epsilon naught. And so if we put these together, we have two forms of Gauss's law. We have the differential form here, and we have the integral form. But the thing to realize here in both cases is that mathematically what we have to assume is that we know the electric field already, because we're taking the derivative of the electric field to give us some charge density. Here we're taking the integral of the electric field to give us a total charge. Another important thing to recognize is that this differential form of the electric field is talking about the electric field at a specific location, at one single location designated by this vector r, this single location r. And it's talking about the charge density at one single location r. In the integral expression, we're looking at the electric field at all points along this closed surface. At every point where that surface exists, we need to know the electric field there. And here we're talking about the total charge within this volume. So whatever charged objects might be inside that volume, we're adding them all up. Okay. So this is another relationship that we can use. And the big question now is, how are we going to exactly use this? If we know the electric field, then we can use this pretty easily to say, okay, well, if somehow I know the electric field, maybe I measure the electric field, that this would let me determine where charges are located. So I can measure the electric field in various locations and start building a map of what kind of charge I have in various regions of space, which can be very, very powerful. So that's one way that Gauss's law can be used. Another way we can use Gauss's law, though, is that in certain circumstances, we can actually use Gauss's law to determine the electric field. To do that, though, we need to do something pretty special because we need to get E by itself, and this is not going to work the way I wanted it to. It's going to try to write E equals, because to determine the electric field, we need to get some equation that then gives us E equals something. That's the goal. But we have a slight problem here. We have E that is a vector inside an integral. And so we need to figure out how to deal with that. So the way we can do this is, if we want to get E by itself, first of all, we would need to be able to take this dot product. And in order to do that, we would need to simplify the dot product by taking that dot product, getting rid of the vector directions. Now, if you remember a dot product, one way of writing a dot product is, let's see if I can do this. So one way of writing a dot product is that you would have to have, for example, E dotted, I'm going to use an asterisk for now, even though it should be a dot, dotted with dA, or rather, let me write it this way. If we had an A vector dotted with B vector, that would equal the magnitude of A times the magnitude of B times the sine of some angle between those two vectors. If you remember that from calculus and previous physics classes, then when you take the dot product of two vectors, oh my goodness, and I've said the wrong thing. This should be a cosine, of course. Maybe you noticed that already. But the dot product between two vectors is the magnitude of each vector multiplied together, and then multiplied by the cosine of some angle. Well, in order to get E by itself, we need to be able to take this dot product and not have any angle left over. So that's something that's important here. And what we need to do then is we need to know the direction of E. But this is part of the goal. So we want to take that dot product, so we have E as a scalar. If we're going to get E by itself, we then need to be able to take E out of the integral. Because if we don't know what E is, then we can't integrate it. So we need to be able to know something about E to be able to take it out of the integral. And then the last thing we need to do is we need to be able to integrate over that surface area. So if we could do all of this, then we would have E times some surface area equals Q enclosed over epsilon naught. We could then solve for E. But to do all these steps requires very specific conditions be met. So we have this equal to Q over epsilon naught. Here's what we need to know even before we do any calculations to be able to use Gauss's law to determine the electric field. I mentioned on Wednesday that Coulomb integrals are always something that we could use, but the mathematics are sometimes prohibitively difficult. Gauss's law in this form is a technique that we can use sometimes. We can't use it all the time. We can use it sometimes. When we can use it, it makes the math much, much easier. And so it's really important to understand when we can use it and when we can't. So to be able to do this, we need to know the direction of the electric field before doing any calculations, just based on the geometry of the problem. That allows us to take this dot product up here. So this is number 1. That allows us to take the dot product, and well, that's part of the reason we can take the dot product. We'll get to the rest of that in a bit. So we need to know the direction of E so that we can take a dot product. We need to know or be able to justify the functional dependence of E. And what I mean by that is E a function of X? Is it a function of Y? Is it a function of Z? Or is it a function of theta or R? And how does E change with position? That's what we need to know. And lastly, we need to choose a specific surface that exploits what we already know about the electric field to be able to make these simplifications. So we need a surface such that E and dA are either parallel with each other or perpendicular to each other for all parts of the surface. That allows us to do this dot product up here. Because if they're parallel, then the angle between them is 0. The cosine of that angle is 1, and we're just left with the magnitude of the electric field times the magnitude of dA. So this surface here that we're left over is where dA and E are parallel with each other. And I'm trying to draw the parallel symbol, and by golly, it's not working very well. There we go. That's not much better, but it's something anyway. So the assumption here is that the surface we have for this integral is the surface where E and dA are parallel to each other. If E and dA are perpendicular to each other, then the dot product is 0, because the angle is 90 degrees, or pi over 2, and the cosine of that angle is 0. So we can break up this closed surface into pieces where E and dA are parallel, and we're left with this integral, and pieces where E and dA are perpendicular, and those are 0. Add them all together, and we're left with just the parallel areas. We also need a surface such that E is uniform across the surface wherever E and dA are parallel. This allows us to pull E out of the integral. So we need to know that whatever this surface is, the magnitude of the electric field is the same everywhere across that. The direction doesn't necessarily have to be the same, but the magnitude has to be the same. And we need a surface that's nice, basically. We need a nice surface. We need a surface that we can determine what the surface area is. That's something that's really important. So I'll talk about an example right now that is one that's sort of canonical for using Gauss's law, which is a uniformly charged ball, or a sphere, like a solid sphere. So if you think about, picture in your mind a solid sphere of charge. For some reason, whenever I picture this sphere, it tends to be yellow. And what I think about when I'm looking at this is that I imagine color indicating charge. So a uniformly charged ball would be the same shade of yellow everywhere around. If this was a ball that had some positive charge and some negative charge, then it would have different colors on the surface at different locations. But in this case, let's just picture it being a solid ball. I'll call it a solid yellow ball of charge. And we can think about, okay, if we take this ball, and for one thing, can we say what the direction of E is going to be? Well, if we think about having a nice ball of charge, then with it being spherically symmetric, if we think about a point out from there, maybe right about there, some point right around there, then we would say, okay, well, for every location on the ball to the left of that point, that's going to create an electric field that's going if this is a positively charged ball, we'd have an electric field going sort of down to the right, but there would be a matching point over on the right that would create an electric field that's down to the left. And for every point on the left, there's a point on the right, and they would all match up together such that these would all add together and give us an electric field that is straight away from the center of that sphere. So if this is the center of the sphere right here, then we would have an electric field that goes directly away from that if it's positive, or directly toward it if it's negative. Okay, and it's because for every point on the left, there's a point on the right. For every point in the front, there's a point in the back, and any way you go, there's always a matching point that those are going to have contributing fields that give us a total field outward from the center of this ball. So we know that E hat will be radially outward from the center. We can call that R hat if we set the origin of the center of the sphere. So that's step number one. Step number two, can we justify the functional dependence? Well, if you picture having this ball and we say, okay, this is a sphere, so if the field is in the R hat direction, maybe we want to use spherical coordinates. So we can think about moving around in various coordinates. So if we move in theta, that would be like rotating the ball along a horizontal axis. So rotating the ball along an axis that looks like this. So the top of the ball would come forward, the bottom of the ball would go back, and rotating it that way. And imagine if you rotate it in that direction, will it look any differently? And well, if it's uniformly colored, uniformly charged, then no, it wouldn't. Turning the ball in that way would not make any difference. If you spin the ball on the other axis, so choose an axis that's sort of up and down, and spin the ball that way, that would be changing phi. And if you think about spinning the ball along that axis, again, because it's uniformly charged, it wouldn't look any differently. It would look exactly the same way no matter how much we spin it. So phi doesn't seem to matter either. But if you think about getting farther away from the ball or closer to the ball, changing the R position, well, that would make a difference. The farther away you get, the smaller it would look. The closer you get, the bigger it would look, and eventually you'd actually be inside the ball. And so that definitely makes a difference, that it looks different where you go. And so that would tell us that the functional dependence is that E depends on R. E is a function of R only, and that's the variable R, not the vector R. So it's not a function theta, not a function phi. So what we want then is we would want a surface such that dA is in the R hat direction for at least some of the surface, and in a perpendicular direction for any other parts. We need E to be uniform across the surface, and so if E depends on R, the value of the distance from the center of the sphere, we would need a surface that has a uniform value of R, so that E would also be uniform. Well, a surface that has a uniform value of R is a sphere. And so we would choose a spherical surface that would sort of go around like this and exist outside our sphere. And the key point here, I did not do a very good job drawing that spherical surface, so I'm sorry about that. Actually, you know what? Let's try this. I'll just see if I can't get this to be a Gaussian surface here. Yeah, that's pretty good. Let's make that a sphere. Alright, that's pretty good. Now, a couple of things that I want to clarify here. first of all, this is an imaginary surface. This is not a real object. That's something that's very important to recognize. That we're making this up. We're using this as a theoretical construct to imagine what this surface would be. And the other thing is, if we want to know the field right here, where I drew my little scribble before, then we need a surface that touches that point. We need a surface such that that point is on the surface. That's what we need. And in this case, because it's a sphere, has to be concentric with our actual charged ball. If I wanted to know the field right here, then I would need to choose a different Gaussian surface. I would need to choose a Gaussian surface that is smaller and touches the ball in there. And there we go. So we need to choose a surface that touches this point right here where we want. So we need to choose a surface inside this ball. Okay, so that's an example of how we can use Gauss's law and how we need to be very careful about how we're using it. In this case, it would work, but if we could not necessarily make those simplifications, then we can't simplify this integral to get an expression for E alone. And so what I'd like you to do now is to take a look at a few different cases. And, oh, wrong way, sorry about that. So this is a sheet that I handed out on Wednesday, and if you weren't there on Wednesday, it's posted on Blackboard. That what I want you to do is to take a look at each of these cases and decide whether or not Gauss's law is going to be useful for determining the electric field. And that's the key. Is Gauss's law useful? Is it a useful tool? Maybe it is, maybe it isn't. For it to be a useful tool, you need to take a look at these criteria from what we were just discussing. What is the direction of E? What is the functional form of E? And what surface should you use? And make sure that you choose a closed surface. That's very important. Otherwise, Gauss's law is not valid. It has to be a closed surface around a finite volume of space. So please take a look at this. Work on it. I encourage you to work with your classmates. But take a look at this activity, and I'll post either another video or a solution set that gives the solutions to these as well. But please make sure you take a look at it on your own beforehand. All right. Have a good one, and I'll see you on Monday.